Alright, this is our first topic, electric charge and electric field. At first, let's talk about charges. There are two kinds of charges in the world, positive charges and negative charges. Here comes the first rule that I want you guys to remember. Two positive charges or two negative charges repel each other, and a positive charge and a negative charge attract each other. One way to remember it is the like charges repel and opposite charges attract. So if we put two positive charges on the table like this, they will repel each other. So this one on the left, it is going to move to the left, and this one on the right, it is going to move to the right. And if we put two negative charges on the table, and this one on the left, it is going to move to the left, and this one on the right, it is going to move to the right. However, if we put a positive charge here and it's a positive charge, you know it, and a negative charge here, they will attract each other. So the positive charge will move to the left, and the negative charge will move to the left. Now I have a question for you. What if I put a positive charge here and a neutral object here? Or what if I put a negative object here and a neutral object here? What's going to happen? There are three choices for you, and one is they repel each other. Second is they attract each other, and the third choice for you is nothing happens. Nothing. So, what do you think? The answer is that in both situations, the charged objects attract the neutral objects. Here are two very important principles. The first one is the principle of conservation of charge, which is the algebraic sum of all the electric charges in any closed system is constant. I hope this principle reminds you of the conservation of energy. They are kind of the same. The conservation of charge means that in any closed system, you cannot create charges, and charges won't disappear. The second principle is the principle of unit, but I don't want to talk about this principle here, and I will mention this principle in a few minutes. I think most of you understand what is a conductor and what is an insulator. Most of metals are conductors, and most of non-metals are insulators. Semiconductors, they are kind of a material between conductors and insulators. They permit the movement of charges through them, but they are not as good as metals. Okay, here comes the most important topic of the day, the Coulomb's law. Remember in the first few slides I mentioned that if we have two like charges, maybe two positive charges, and they will repel each other, and two different charges, a positive charge and a negative charge, they will attract each other. And I hope you realize that there have to be forces act on both charges. And this force is called the electric force. And Coulomb's law is going to help us to figure out the magnitude of the electric force between 2 point charges. Remember, it's 2 point charges. Based on lots of data, Coulomb finally realized that the magnitude of the electric force between 2 point charges is related to the product of the charges and the square of distance between them. I hope this remind you of something. Remember when we studied about gravitational potential and the gravity? Remember, the gravity between two stars is related to their mass and the square of distance between them. So we really hope that we can get a function that is kind of look like the same with the gravitational gravity function. Here's a function of gravity. F of g equals to uh, g constant times 2 mass m over r squared. And here's the f we are looking for. Instead of g, we have another constant, we call it k. Instead of mass, we use charges, q1, q2, over r squared, r is the distance between two charges. Well, here is an example. If we have two like charges, maybe two positive charges, and in this case they will repel each other, and we call this charge 1 and this charge 2. The force act on charge 1 is because of the exist of charge 2, so we call this force F2 on 1, and vice versa, we call this F1 on 2. According to Newton's third law, F2 on 1 should equal to F1 on 2. F2 on 1 should equal to F1 on 2, which equals to F equals to K Q1 Q2 over R squared. In this case, Q1 is just the charge of charge 1, Q2 is the charge of charge 2, and the R is just the distance between charge 1 and charge 2 at that moment. Oops, sorry, I need to put absolute value here. For here, I consider F as, I only consider the magnitude of F. And before we talk about the constant K, I'd like to talk about the unit of charge. The SI unit of charge is called 1 Coulomb and denoted as 1C. Now let's go back to the second principle, the principle of unit, which says that the most fundamental unit of charge is the magnitude of the charge of an electron or proton, which is denoted by E. And E equals 1.60 times 10 to the negative 19 Coulomb. Now let's talk about the unit of the equation. The electric force, the unit of electric force is Newton, and the unit of charges are Coulomb, and the unit of R is meter. So if the question gave you the charges in the form of E, maybe such as the alpha particle has charge 2e, you need to convert 2e into Coulomb. In this case, it's 2 times 1.60 times 10 to the negative 19 Coulomb equals 3.2 times 10 to the negative 19 Coulomb. Now let's talk about the constant K. We usually take K equals to 8.988 times 10 to the 9th Newton times meter square over Coulomb square. And one interesting thing is that usually in SI units, we write the constant K in the equation as 1 over 4 pi epsilon 0. And epsilon 0 is just another constant. So instead of writing F equals K Q1 Q2 over R squared, we usually write this like 1 over 4 pi epsilon 0 times q1 q2 over r squared. And although there's no reason why we do this here, yeah, but this actually will simplify our equation in the future. Well, actually, most of the time we take 1 over 4 pi epsilon 0 equals to 9.0 times 10 to the ninth Newton times meter squared per Coulomb square. And we will use this number in the actual problems a lot for it's easier. Please pause this video and try to figure out this question by yourself, and I will give you the answer in a second. The question doesn't give us a distance between the 2-point charges, but that's okay. For we're looking for the ratio of these two forces, so we can just cancel out the distance. Actually, the distance square. And finally, we get 3.1 times 10 to the 35th, and I hope you get the same number. So this is a really large number, and I think this can give you a concept that when you have two particles, the electric force between two particles is actually larger than gravity, and sometimes we can even ignore the gravity in the problems. Try to do this question by yourself, and I will give you the answer in a minute. I hope you realize that this is a symmetric problem. For at first, the distances between Q1, Q2, Q1, Q3, and Q2, Q3 they are the same. And second is that the charges of Q1 and Q2 they are the same. So actually, the magnitude of F1 on 3 equals to the magnitude of F2 on 3. The reason is that in the equation of electric force is 1 over 4 pi epsilon 0 times Q1 Q2 over r squared. And here the product of charges Q1 times Q3 and Q2 times Q3 they're the same, and r squared. And the distance between Q1 Q3 and Q2 Q3 are the same, so the magnitude of force they're the same. Now we need to consider this problem in two dimensions. What happened in x direction is that we have two equal force components in x direction. In x direction, F1 on 3 equals to 0.29 times cosine alpha equals 0.23 Newton, but that's also equals to F23 in x direction. So the net force in x direction equals to 0.23 Newton times 2 equals to 0.46 Newton. In y direction, the components of force they have the same magnitude but opposite directions. So actually they cancel out. So the net force in y direction equals to 0. So the answer for the problem is 0.46 Newton, and direction is to the right or to the x direction.